let's take a step back and think about the gravitational force. Now, in Newton's day, they didn't know that the force. They didn't know all that much about the force of gravity. So, in Newton's day, they figured that well, the force of gravity. It would make a lot of sense if it was some sort of GMM on the top here. We'll talk about that in a second. Divided by R. But they didn't know what number that was. Okay? So in Newton's day, they figured that, well, if there's some force of gravity, some force of gravitational attraction, then it would make sense if it was larger, if the mass of the sun was larger, right? It would make sense if the force of this gravitational attraction was larger, if the planet's mass is larger. And it would make sense if there was some sort of overall strength to the force. There's some constant that determines the strength of that force. And it would make sense if this force depended on the distance, r, the distance between those two objects. But they did not know what this number is for r. And so in Newton's day, they didn't know what that number was, but they did know that the planets had elliptical orbits. And so a grand challenge to all the academics everywhere was to try to figure out what this number was from the fact that the planet orbits are elliptical. Now, Amy, do you know the trivia about how Newton figured this out? Figured out what that number is? What did he do?
He invented something.
He invented something
fabulous.
Something that has annoyed and frustrated students for decades, right?
That would be calculus.
Calculus. So he invented calculus in order to do this. Now, the reason he invented calculus is because he didn't have a computer.
But we do.
But we do, and so we can do what Newton did in a couple of minutes without having to invent calculus.
Right.
And in this exercise, in this activity, we haven't used calculus yet, right?
Not one bit.
And we're not going to use calculus. We're just going to let the computer do the work for us. And what we're going to do is we're going to see if for different numbers here, what kind of orbits do we get? Do we get elliptical orbits? Do we get something else? And we can use that to figure out what that number is.
Right. So we know that the actual answer is 2. But if we vary that 2, we'll see what it does.
Right. So before we go into the code and just try it out, what we can do is just kind of think to ourselves, what would it mean to have a different number here? Like, what would be the ramifications of that? So we know the correct answer is 2, so I'm going to ahead and stick a 2 in here. And if I switch over to the code real quick, just to see this thing, if I'm going to hit play, so you can kind of see, so we're doing an orbit there. And we start out kind of far away, but then we get closer. We eventually get kind of over here. Now, let's say that the distance between these two things at closest approach, let's say it's like 50. There we go. Let's say it's like 50 when it gets to that point. Okay? So if we were to kind of write that down.
So that makes our R 50.
Right.
At closest approach.
So at closest approach, it's going to be 50 squared. And what is 50 squared? You can do that in your head?
2,500.
2,500, very good. All right. It's a little early, but I think I agree with that. 2,500. But what would it be if the r was, if instead of r squared, what if we had an r to the 1.5? Do you want to?
Okay, yeah, so r to the 1.5. I'm going to do math magic in my head.
There you go.
Our GMM over 50, but this time to the power of 1.5. This is equal to GMM, the easy part, over 353.
Yeah. And we didn't do that in our heads. We did that.
No, I did it in my head.
Okay. All right. Maybe you did. I don't know how to do it.
Okay. So that was GMM over r to the power of 1.5. Maybe you can do GMM r to the power of 2.5 in your head?
I don't know if I can do that. So r to the 2.5, so that would be GMM over 50 to the 2.5.
So we've increased our exponent.
Right.
What do you think should happen to the...
And do I think it should be... All right, so this one is 2,500. So if we decrease that number, we get a lower number. I'm going to guess that if we increase this number, we get a higher number.
Right.
And, oh, look, on the side of the board, it has the answer of what this is. It's 17,678 is the answer. Okay? Again, I can't do that in my head. Maybe you did. I don't. Maybe you're a super genius. That's what we get. So when the planet comes and it's close to the sun, which one of these gravity models has the strongest force when the two are close together?
The strongest force would be the one where the denominator is the smallest here.
Right, and then the weakest force would be this one, right? Because we're taking GMM, we're dividing by this huge number, right?
Right, makes our gravitational force pretty tiny.
Yeah, and then this is kind of in between the r squared. And so when we put this into the code, let's look carefully at it to see if we can kind of notice the way that the trajectories are going to get bent by the fact that the force here is much stronger closer to the sun than it is for these other power laws. So this should have an effect on the orbits. Would you agree?
Yeah. So we've done maths. Now we need to check and see if it works out on our cartoon.
Right. All right. Let's go back to the code then.
Okay, so now we need to alter our code so that we can change our r to a power, to different powers. So we have this n power equal to 2 here, and then the f grav down here where we can change the power. So I'm going to copy that to the clipboard.
Yeah, so instead of r times r, we're going to have a pow function and then an exponent to that power.
Right, and I'm just going to, going to comment out our old thing here, paste in our new one. All right, so we have a variable n power here. I need to actually go up and make sure it knows what that variable is. So we'll put it in down here.
Yeah, so if you put 2, it should give us exactly the same behavior as before, right?
Right, so 2.0. We'll push play and see how that goes. All right, that looks pretty much the same. So remember when we said that we decreased this power, 1.5, that gravitational force at closest approach was the smallest number. So that should increase our force. Let's see if that works. So at closest approach, the magnitude of that vector was a lot greater. Now, notice our closest approach is actually changing because we're no longer on an elliptical orbit.
Right. And so we definitely don't get an ellipse from this, right?
Right.
And one of the things you should do is try to launch the object and try to get an ellipse out of this, right?
Okay, so we can change that.
That doesn't look like an ellipse to
No.
me. If you wait long enough, it'll probably
come back around.
come back around.
It's a cool shape.
Yeah.
But it's not what we want. Okay, should we try a larger number now?
Sure.
All right, so let's change our n power to 2.5. And this is the one that we said should give us the smallest force of gravity at closest approach. So we'll see what that looks like.
we go. Whoa. That's interesting. That's definitely not an ellipse. Yeah, maybe see if you can launch it again. Like, part of the fun of this activity is saying, okay, well, that doesn't give us an ellipse, but is there any way you can get an ellipse out of this thing, right? Because the planets in the solar system, they seem to be on elliptical orbits, but is there any way that that elliptical orbit could happen with some other number in that force law?
Right.
And so you are encouraged to play around with this thing for as long as you want.
Woo.
Just try to figure out if you could do an ellipse. And I think the answer is that you can't, but you should try. You should try to see if you can get an ellipse out of it. The planets in the solar system definitely don't do that, right?
No, definitely not.
So again, Newton had to invent calculus to figure this sort of stuff out. He didn't have a computer, but in not too long, we managed to come to exactly the same conclusion.
Okay, so we've finished up our activity. If you want to read through these last few sections, there's some interesting things there that you could look at and learn. But that's pretty much it for us today.
Thanks for your help, Amy. Thanks for hanging out with us.
Happy to.
And we can let you get back to your dissertation about galaxies and all that stuff. So
I'd love to do that.
All right, well, thanks for tuning in, everybody. Subscribe, for goodness sake, subscribe. But thanks for coming. And we'll see you next time.
Bye-bye.